another topic that we're interested in is really this assembly of materials on surfaces. So we use a process known as electrophoretic deposition, which is where an electric field will deposit a charged particle on a surface. And we really feel like this is a nice bridge between a lot of the wonderful work being done at the nanoscale and what's needed to scale up devices to larger scale, more engineering practical applications. So what do we mean by that? Or what do I mean by that? Anytime you take a nanoscale particle or any particle and you put it in a solution, generally speaking, they're going to develop some surface charge naturally. So if you take glass and you put glass in contact with water, glass will actually act like an acid and donate protons to the water, and you'll get a negative charge layer on the surface of the glass. If you have a glass particle, now you have a surface that's negatively charged. If you apply an electric field, that particle will move. And so you can deposit glass and nearly any other particle which will develop a surface charge onto electrodes or onto oppositely charged surfaces just using electric fields. And so we're developing techniques where we use this process in order to change the properties of surfaces. So we've made surfaces super hydrophobic simply by taking particles that were hydrophobic and assembling them very easily and at potentially low cost using electric fields onto various substrates. So we've done this on fabrics, we've done this on metals, we've done this on porous media. The only requirement is that the substrate has electric field lines which are perpendicular. So electric field lines which will effectively go into the substrate, which is true for a conductor, or if you had a porous medium where there's some pores which allow fluid to flow through. Some of the places where we see this is potentially imagine applying coatings to ship hulls. So a big problem in the shipping industry is biofouling. So for example, the Navy spent a considerable amount of money, or a considerable amount of money is wasted on fuel due to increased drag on ships due to biofouling. And so it's one of the biggest problems that they've been working on for decades now. Now there used to be coatings that they could apply which included copper, which was very effective. The problem is that this copper would leach out into the water and kill some of the local biology. And so now there's a big push on going to more environmentally friendly types of coatings. And so the things that we deposit are environmentally friendly. They effectively use mechanical properties to prevent adhesion rather than chemical properties. So the fact that we use this electrophoretic deposition, it allows us to take these very micro and nanoscale effects, those are the scales needed if you want to prevent something like biofouling, but you need that effect over meters squared of area. And so this electrophoretic deposition technique very easily scales to meters squared. So one place where this is already used is in automobiles. So roughly 95–98% of automobiles are already coated with their first coat of paint using electrophoresis. They actually dip the metal parts in a bath and will deposit particles using this effect. So if it's scalable enough for the auto industry, it should be scalable enough for other industries. Thus far, it's only been applied to paints though. It hasn't been applied to specialized surface coatings for things like preventing biofouling or superhydrophobicity.